Somewhere in your life, right now, a rotor is spinning within microns of a wall it must never touch. The compressor cooling a factory, a steam turbine feeding a power grid, a wind turbine bearing 25 years into its life. Drift by a few microns and the machine destroys itself in seconds. Watch how humans build parts that stay this close to disaster on purpose and never actually get there. A giant industrial screw can be several meters long and weigh tens of tons. But the reason it is one of the hardest parts on Earth to make has nothing to do with size. It is the shape, a continuous three-dimensional helical form that has to be exact along its entire length. Miss by a few microns and a compressor loses efficiency, a pump leaks, or the rotor shakes itself apart at thousands of revolutions per minute. And that is why the world builds entire specialized CNC machines whose only job is to shape one type of part. Rotor milling machines can cut helix profiles on blanks up to 850 millimeters across, some as large as a meter in diameter. Every step exists to protect the geometry. Rough milling first, then heat treatment to relieve internal stress, then precision grinding to bring the surface within microns of the target, then coordinate measuring machines, dial indicators, and air gauging to verify the shape. The machine has to be more accurate than the part it makes. If it is not, you get scrap. Very expensive scrap. Zoom in on what actually happens on the machine, and the difficulty gets easier to see. A steel rod goes into the chuck. The cutting tool moves along the length while the rod rotates. But the tool does not just cut a spiral groove. The tool follows a computed path that changes angle, depth, and speed at every point along the surface. The rotation and the cutter feed have to stay perfectly synchronized. If the synchronization drifts even slightly, the helix gets uneven, and the whole part is finished before anyone knows it is wrong. You cannot fix a bad screw. You can only start over. Watch it happen up close, and it's weirdly relaxing. A 90mm screw for a plastic extruder gets milled with helical grooves running down its length. Sparks, metal shavings, slow, controlled cuts. Every pass shapes another few millimeters of a form that has to be perfect. What decides whether the finished part actually works? People think CNC creates precision. It does not. CNC only finishes what has already been prepared. A billet with the wrong internal structure will never become a precise part, no matter what machine touches it. Take this 13-inch forged valve body. Before any cutter touches it, the steel already has to have the correct grain flow, the correct density, and no internal defects. The most expensive machine in the world cannot fix a bad billet. Roll forging shows the principle at small scale. Hot steel plates pass between rollers that squeeze them to the required thickness. The heat lets the grain reorient. The pressure forces internal fibers to align along the direction of the finished part. The same idea, scaled up, is how rotor blanks and heavy shafts get their strength. Grain flow along the load direction is what keeps them from breaking under torque. And when the finished part weighs 50 tons, the material prep becomes its own factory. Massive rolls used in steel mills start as cast metal poured from a foundry, then move through heat treatment, machining, and multiple stages of testing before they are ever certified for use. Ultrasonic testing checks for hidden cracks buried deep inside the metal. Measurements taken with calipers verify the outside dimensions. Furnaces slowly bring the temperature down over days, so no internal stress remains locked in. 200 years of experience goes into knowing exactly how long that cooling has to take. Rush it, and the roll cracks itself apart the first time it takes a load. Now for the part that catches most people off guard. Making a huge part often requires a machine that is even bigger. This horizontal turning machine holds a workpiece so heavy the chuck alone weighs several tons. Sparks fly, coolant floods the cut. The workpiece stays put and everything else moves around it. The bigger the part, the more the machine has to be built like a bridge. An 800mm swing over 6 meters of length, live tooling on an 8-station tool changer. Every axis has to move without vibration, because the smallest wobble at this scale ruins the surface finish and throws the tolerance out. Now scale that up to a plate you have to move with a crane before machining can even begin. A metal slab gets chained down to the machine bed. A heavy milling head rips through the surface, throwing off colorful shavings in every direction. The material removal rate is enormous. So is the heat, the force, and the vibration. Everything about this operation is trying to move the workpiece. The setup exists to convince it not to. And when the part is a crankshaft, the machine has to work in 2 directions at once. A horizontal turn mill mounts the crankshaft along its axis, while the spindle head moves vertically to reach each throw. Coolant floods the cut. Chips fly off in ribbons. Every offset gets machined to the same tolerance the CNC uses to move, which is the whole point. Some parts need hundreds of holes drilled around a circumference, each one placed to a fraction of a millimeter. A deep hole drilling operation on a large stainless cylinder works through the entire circle without stopping, coolant spraying the whole time. Miss one hole by 1/10 of a millimeter and the assembly it goes into will not close, so it does not miss. Not every surface is a flat or a cylinder. Some geometries are so complex that a normal CNC cannot even attempt them. A crankshaft is the classic example. Offset journals, weighted counterbalances, oil holes drilled at angles into the throws. Every one of those journals has to end up perfectly concentric with the main rotation axis while sitting off-center. That requires the workpiece to rotate around one axis while the cutter tracks around another. 2 synchronized rotations, working at the same time. If you have ever tried patting your head and rubbing your stomach at the same time, this is like that, but in steel, under load. And the newest generation of machines does the whole crankshaft in a single setup. A mill turn center holds the raw forging on one end, then works down the length turning journals, milling counterweights, drilling oil galleries, and cutting keyways without ever unclamping the part. Why does that matter? Because every time a part gets unclamped and reclamped, the reference position shifts by a few microns. Do that 5 or 6 times across a complex crankshaft, and the accumulated error becomes larger than the tolerance you were trying to hold in the first place. Doing it in one setup eliminates the entire error stack. The part gets locked into place once, and every feature is machined relative to that single reference. That is why complete machining in one operation is not marketing. It is math. You cannot beat error accumulation with better skill. You can only avoid it entirely. Now the same idea gets pushed further with 2 spindles working simultaneously. A flexible shaft machining setup uses an war spindle that moves along the x-axis while a coordinated tailstock supports the far end. Upper and lower turrets perform superimposed operations at the same time. One side turns while the other drills. One side mills while the other taps. Grooving, threading, chamfering, cutoff, and part transfer to the sub-spindle all happen in a continuous sequence. Watch the drilling operations. 2.5mm drills going in from opposite sides at the same instant. Tapping meters 3 threads simultaneously. Then a 12mm mill cutting on top while a groover cuts on the bottom. Every axis is doing something useful. Every second the machine is running. Idle time is money that already left the building. The cycle finishes with the finished part being caught, washed, and unloaded without a hand ever touching it. Gears are a category all their own. Cutting a gear tooth means machining an involute curve, a shape that is easy to describe mathematically and almost impossible to execute mechanically. Power skiving solves it. The cutter and the workpiece rotate at exact ratios to each other, and the tool geometry itself carries the involute shape. As they rotate together, the tooth form gets cut by the interaction of the 2 motions. Both external and internal gears can be cut this way. Chamfering, deburring, and pointing all happen on the same setup. The math is doing most of the work. The machine is just holding the tool steady enough to let it happen. And when the gear is too big for a normal machining center, the process has to happen in phases. A large gear gets rough cut over several sequential operations, each one removing more material than the last. Coolant floods the cut. Chips pile up. Each phase brings the tooth form closer to final. And then there is the rack, a gear stretched flat. A precision rack milling machine cuts teeth along lengths up to 4.1 meters, either one at a time for prototypes or in gangs of multiple cutters for production. Every tooth has to match every other tooth, because if they do not, the whole rack skips. Machining is not the last step. Heat is. An induction hardening machine can harden external gear teeth up to 5 meters across, bringing the surface to 52 to 56 on the Rockwell C scale. Hard enough to shrug off decades of load without wearing the tooth profile away. And heat does not just harden, it also assembles. Large industrial gears get shrink-fitted onto shafts using thermal expansion. Heat the gear, and the bore grows by a fraction of a millimeter. Slide it onto the shaft while hot. Let it cool. As it shrinks back, it grips the shaft with a force no bolt could match. The same heat that ruins tolerance also creates it. You just have to time it right. A rotor that looks flawless can still get rejected. A coordinate measurement arm sweeps its probe across the tooth flank, collecting thousands of data points. Every one of them gets compared to the design. Runout, concentricity, profile deviation. If any measurement drifts past a few microns, the part goes back for rework or the scrap bin. Static measurement is only half the answer. The real proof is when the rotor spins. Instrumentation and probes fill the test rig, capturing pressure, temperature, and vibration in real time. A part that measured perfect at rest can still fail once loaded. All that precision has to end up somewhere. So where do these parts actually go? Watch one of the largest screw compressors ever built come together. 2 matching helical rotors get lowered into a casing that has to hold them within microns of each other, because if they touch, they destroy each other in seconds. The factory where machines like this get built looks less like a workshop and more like a small city. Machining, welding, coating, quality control, warehousing, and assembly all happen under the same roof. Robotic high-velocity oxygen fuel, spraying coats parts with wear-resistant surfaces. Large lathes, machine compressor rotors. 3-dimensional measuring systems verify every dimension. Impellers get welded, then trimmed and balanced. Steam turbines up to 24 megawatts get assembled here for power generation and marine drives. You could probably run a small country from what leaves this loading dock in a year. Now the same principles applied to something the size of a house. A gantry-type milling machine works on a marine diesel engine block so large that the machine has to move over it. Automated tool holders swap cutters mid-operation. Coolant floods every cut. The block gets bored, milled, and drilled to the tolerances a piston needs to move up and down billions of times without the cylinder wall ever noticing. Wind turbines run on precision bearings so large they need their own dedicated machine tool. A vertical turning center machine's the raceway of a slewing ring bearing, the massive circular bearing that lets a turbine nacelle rotate to face the wind. Metal shavings pile up as the cutter takes down the surface. The raceway has to end up perfectly round to within microns, because it will support thousands of rotations under enormous load for the next 25 years. Not every precise part is a giant, but every giant machine depends on thousands of smaller ones being right. Watch AV12 engine block get milled from a solid billet using high-feed cutters. Face milling roughing first, then face milling finishing, then helical interpolation to cut round pockets, then pocket milling to open up the water jackets and oil galleries. One cutter, multiple strategies, all working the same block from raw material to finished shape. Every operation removes material at controlled rates, keeping cutting forces stable so the workpiece never deflects. The tolerances that make an engine run smoothly get built into the block before a piston ever slides in. Live machining demonstrations show what a modern part looks like from start to finish. A single component goes through dynamic milling, pocketing, drilling, reaming, and finishing operations. Each step handled by a different cutter chosen for the exact operation. Alloy steel around 40 on the Rockwell C scale gives every cutter a real workout. The material is deliberately challenging. Precision machining is not about one clever trick. It is about picking the right tool for each of dozens of tiny problems in the right order, without letting one mistake ruin the previous 15 steps. And sometimes the precision goes into something you can actually recognize. A robot head gets milled from solid metal for a museum exhibition. Curved surfaces, drilled features, and finished details all come out of the same cutting technology used on gear, teeth, and turbine blades. The tools do not care what the shape is called. They just cut. Behind every finished gearbox is a design office, a machining floor, an assembly hall, and a quality control lab all working in parallel. Engineers build 3D models. Machinists cut the parts. Assemblers stack the shafts and gears together. Then inspectors take over, coordinate measuring machines, tachometers, infrared thermometers, probes checking tooth flank profiles at hundreds of points. A gearbox that will run for 25 years in a mine or a mill has to leave the factory knowing it will do exactly that. Nothing gets shipped on hope. Every dimension gets verified before the crate closes. When the gear is going into a critical drive, the process gets stretched across every technology available. Advanced gear cutting equipment, precision heat treatment, dimensional measurement to microns, load testing under simulated operating conditions, all under one roof, coordinated as a continuous chain. Every step exists because the next one downstream cannot afford surprises, and nothing gets shipped until every step signs off. Precision is not just about making new parts. It is also about fixing old ones. Gearbox rebuild and repair takes a worn-out drive apart, measures every surface, and machines back to original tolerance. Some of these gearboxes have been running for 40 years. The rebuild is what buys them the next 40. Threading is one of the oldest machining operations there is, and one of the hardest to scale up. Threading inserts for extra-large pitches up to 24 millimeters cut coarse threads on heavy-duty parts. Every pass has to match the last one perfectly. Threads that do not line up will never assemble. Now, the same precision principles get scaled up to something that reshapes an entire steel plant. 3 basic oxygen steelmaking converters get replaced with larger ones to raise output from 5.4 to 6.0 million tons per year. Every stage of the project rests on precision. 3D CAD models coordinated with the physical facility. Stress analysis on suspension components. Diamond wire sawing through the concrete foundation to make room for new bearings. Then the actual assembly. Shrink fit connections between drive shafts and bearing housings, tightened with hydraulic pressure. Suspension bearings machined and installed to hold hundreds of tons of hot converter without shifting even slightly. Every dimension measured. Every joint verified. Then the first heat of molten steel goes in, and 4 decades of production begins on a system that has to hold precision the whole way through. Precision does not only apply to spinning parts. Chain links for heavy lifting get forged from hot steel, welded into loops, tested to failure, and painted for identification. Each link has to hold its rated load exactly. Weakest link problems are not metaphors when the load is 50 tons overhead. Small parts, big precision demands. A brass cylinder gets slot after slot milled around its circumference. The The finished part will be a vacuum sizing die for plastic extrusion. Every slot has to be identical, positioned exactly and dimensioned to microns. Miss one, and the die pulls the extruded profile off-center. Precision engineering is not about one clever machine. It is about a whole ecosystem where every stage has to be right for the next stage to work. A rotor is only as accurate as its billet. A billet is only as trustworthy as the forge that made it. A finished gearbox is only as strong as the assembly that shrink fits it together. A single measurement drifting out of tolerance early in the process can quietly follow a part all the way to final assembly. That is why inspection never belongs to just one station. It follows the component from raw material to finished product. Modern debates in this field circle around automation, closed-loop tolerancing, and whether AI-driven adaptive machining will finally close the gap between simulated and actual part accuracy. Modern factories now collect millions of measurements that would have been impossible to track a generation ago. Some argue human machinists still catch things algorithms miss. Others say automation is overtaking that advantage fast. The next generation of factories may spend as much time analyzing data as cutting metal. Where do you land? Do you trust an experienced machinist over an algorithm, or the other way around? Let us know in the comments. Precision will always be measured on the part itself, not on the computer screen. Thanks for watching, and hit subscribe to see more of the machines that keep the modern world running. See you in the next one. Take care.